Give you started, the agenda of today's webinar. The next slide will talk about the purpose, what's included in the webinar. We'll talk about some advantages of energy storage, the integration of energy storage into PV plants and connecting them, various applications and capabilities of PV plus storage plants that you can take advantage of today. And finally, the various solutions that Inga Team does provide and take to market in our products to provide the solutions for these applications. So the purpose of this presentation is to discuss grid-connected applications which are utility scale, larger in size. They will be PV plus storage plants taken into consideration, and a lot of my slides are going to focus on ramp rate controls for a PV plus storage plant. However, globally speaking, there are many different advantages in plants which can connect with PV plus storage, while a lot of my slides and visuals will show mostly focus on ramp rate controls. I want to emphasize though, however, that this presentation really is not focused around a microgrid application or voltage and frequency forming solutions. These small residential plants or just storage alone, I want to provide a focus on what this webinar is related to. So, what are some of the effects while incorporating a storage system into a PV plant? There are advantages you can gain. So you get the ability with having, compared to a standard PV plant, a greater availability in grid quality and grid support functionality that you can have by accessing the PV and or the storage inverters. The flexibility during a irradiance drop due to cloud cover over a PV and renewable plant allows you, adding a storage system, more flexibility of your plant. In addition to that, while you have more PV penetration on a grid system, especially for medium and small grids, the addition of storage allows a deeper penetration of renewable energies. And with that increase of renewable energies, it allows more power generation sources compared to that of fossil fuels, and allows that mix of power supplied to the grid to be increased of that of renewable resources. And this can allow for cost savings to a grid operator. So in a standard PV plant, what's realistically available today? Just PV alone, not considering a storage system addition. Today, you do have access through the inverters to have reactive power, high voltage, low voltage ride-through capabilities, and even reduction of active power or curtailment onto a PV system. But as increased PV penetration and a higher demand for grid stability, and as grid operators try to get a mix of their power generation more closely aligned with that of consumption, you need to consider that higher PV penetration, the ability to add storage to that PV system, is needed. Here is an example of a control option taking into account ramp rate control. It allows the grid operator to more smoothly integrate that generation source during the peaks and valleys that of a PV system. There are utilities which have applied this onto their grid system. Puerto Rico, Mexico right now is doing a program that they're considering for ramp rate controls on their grid system to help for grid stability. It allows, with PV alone, a ramp rate up capability today, but in order to get any sort of ramp down functionality, a storage system is necessary when you do have loss of irradiation on a PV plant. Another control option that is being taken advantage of in the world today includes also a PV firming. In this example of control, you're taking into account weather forecasting, and you're doing predictive analysis to tell the grid operator between time A and B, I can give you, the system, a consistent power output, similar to that like you would a natural gas plant or any other fossil fuel plant. You have constant power output, irregardless of what types of irradiation losses, because you've introduced a storage system to take that into account. We particularly have installed 2 of these systems, one in the Indian Ocean and one in the Caribbean. I'm going to spend a little time on this slide because it's very important, and I cite the source of that, which is available to you. But over a year's worth of data collection is taken into account. To also take into consideration that when you're considering a larger area of a PV plant, as you see along the x-axis of the curve, there is less variation across the entire PV array due to the larger size. And when you take this into account, and a key takeaway from this is when you're considering especially a ramp rate control scheme, you could consider that there's less demand and sizing of batteries to take into account for that variation in power, which you have that demand for the batteries when you want that control scheme to the grid operator. So let me paint a picture for you here. For example, if you visually like to see a PV array in front of you. These are multiple strings, PV panels, PV inverters in them. I just want to try to give you a visualization here. Let's paint over the top of that, if you will, a grid. Each one could account for 1, 2 megawatt PV blocks. Pretty common what you could see in a PV array, interconnected into a grid. So we'll keep the grid for you just for visual representation, but we'll get rid of the picture, make it easier. So let's consider a PV alone system. Now, also taking into account in what is the best design of a plant, in a distributed system, if you're taking into account each individual 1 or 2 megawatt block of PV, a PV plus storage system per in a distributed system versus later I'll show you pictures that of a centralized philosophy of a PV plus storage system. Here again, each individual 1 or 2 megawatt block considered as a distributed philosophy for connecting, versus that in this slide where you'd see a central, taking into account then the entire PV array alone acting as a PV connected to multiple inverters, and one singular connected system for the DC batteries. With the centralized system, because it has a larger area, if you take it all into account, and if you remember back to the previous slide, seeing less variation, you have in a large centralized system the consideration of a holistic plant of PV plus storage to take advantage of the entire array, having less variation, making your demand for DC battery sizing and design less demanding on your entire system. And taking into account in the distributed system of a DC battery plus PV array, you have the potential demand because of the operating voltages of each individual component, the batteries versus the PV array, of different operating voltages. You would have the demand of having DC to DC converter, common DC bus, before the final DC to AC inverter connected to the grid. So if you take that all into consideration, an AC coupled large PV array in a centralized system has advantages of utilizing standardized inverters. That's a key. The efficiencies and sizes of those inverters are similar, but the larger array causing less demand of sizing of batteries offers less cost because of less battery equipment is required. Therefore, we discovered that a AC coupled and a centralized system being that of a more optimized system. Now, how further can you additionally optimize that centralized solution? If you take into account just the DC batteries and just the PV array, how can you optimize each system? In the PV, because they're the same inverters, we have the capabilities of connecting up to 3 PV inverters or 3 battery storage inverters into a single low voltage winding of a step-up transformer. Therefore, an additional optimization of the entire plant could allow you to reduce even further, potentially, the demand of the number of transformers that could be connected to your system, because you're optimizing each one individually. The PV optimized, the battery system optimized. Reduction of equipment, additional cost savings. And finally, when taking into account the centralized system, and what's also a benefit to batteries, if you consider the irradiance on a centralized system versus that of a distributed system, you have the clouds that are going to come over. When it has no clouds to this first moment, now you've got clouds over your array. In a ramp rate control scheme, this is the time where the DC of the batteries is operating to give you the ramp rate control down while you lose irradiance on your array. Versus that of a distributed system, though, as that cloud passes through your entire array, a distributed system would require the next stage, the next grid, if you will, that it needs to operate those batteries again. However, in the centralized system, it's already operated. That cloud is passing continuously, but the same effect has taken place. Therefore, you actually have less total cycling of your batteries, thus keeping your battery life extension of your entire system, an additional advantage. So in summary, and especially taking into account the ramp rate control, you do have, with the cloud behavior, you get to take advantage of, in a centralized large system, that larger area. You have less power variation, therefore you have less quantity of batteries demand for your entire system. And as you have that variation passing of a cloud cover once through your entire array, you have less demand on your batteries, therefore extending the life cycle of the battery system as an opportunity for you. Lower battery powers, as mentioned above, requires that less capacity, therefore less number of battery inverters. And in that centralized system, take advantage of standardized inverters. The PV inverters are standardized, the storage inverters are standardized. I'll explain further some of the inverters in our product line later. And when you consider that power station effect of connecting 2 or 3 of each inverter style into one transformer, you have less balance of system equipment. All of these having a cost savings to your entire plant operation. Now, to dynamically control any plant, whether it be PV plus batteries plus even a diesel genset as an option to you, a plant controller is required to have that dynamic power to measure at that point of interconnection. What is available today for applications and capabilities of an entire plant control? I did talk about ramp rate control. Also available is that reduction or movement of that absolute power up and down of the entire plant. Changing a production as the array that the utility might want to take advantage of. You have over or under frequency, you have the capabilities to measure that and curtail the active power on the grid system. Voltage control, reactive, active power controls, and power factor controls to help stabilize the grid operator are additional controls that you gain by implementing a plant controller on the entire system. How our plant controller takes into account the status and the modification of the entire array. So the plant controller at the point of interconnect is continuously measuring the status of the system. Then, when the SCADA or the utility operator is going to send a different operating mode, sends it into the plant via the plant controller. That plant controller is going to calculate in its algorithm the new set points that need to be met at the point of interconnect and run the control algorithm, finally sending the inverters, each individual inverter, the command of what it needs to do until each inverter is met at the new set point. A few, but not all, of the examples of capable controls that are out there: reactive power adjustment of active versus reactive power. Dynamically, the inverters have the capability in reactive power control for grid support or power factor control for grid support, the capabilities to make adjustments to the inverters via the plant controller. Here, an example of that absolute power. The grid operator may need curtailment as an example. This is an example, and I'll spend a second on here, the red being the power output to match what the new set points in the dark blue that are sent by the SCADA of the utility operator to the individual plant to go up or down in active power as necessary that he or she, the plant operator, requires. Here is an example of ramp control where the new set point is sent to the plant, and as a power percentage over time as specified by the grid operator, you can see the bounds of which the actual plant is able to achieve to meet the new set points set by the grid operator over the duration of time that he or she requests, down and up. And one of the additional pictorials of the applications that could be achieved with the addition of the plant controller on a plant is during an over or under frequency event, the ability of a plant to adjust its active power to help support the grid operator control his grid. And in discussing what are the solutions that Ingeteam is capable in its products for the PV plus storage plant, includes Ingeteam provides a plant controller. We have the capability of providing PV inverters, the battery inverters necessary, and that system optimization of power station for both the PV or the battery system. The plant controller acts as that access into the entire system from the grid operator. From a SCADA system, it's the point that he's communicating into the entire plant. If in the case of a PV firming application, it does the forecasting and calculations, and is the device which sends the active and reactive power commands into each individual inverter in the entire system. And also from a communication standpoint, always receiving from the battery system status of charge and all the parameters which the battery system needs to operate from the battery BMS. All that is running through the plant controller. For consideration of PV inverters, what's available in the market in consideration of a 1,000 volt system. I'll show a 1,500 volt next. Typical sizes that are available in the market, at least for our product line, includes anywhere from 610 to 1165, and with an output up to 420 volts. And for a 1,500 volt product line, ranges in power anywhere from 1170 to 1640 kW in power range. This entire family, included with the next slides of our battery product line, come from the same family of products. For our 1,000 volt storage system, it also includes battery inverters, which are rated 610 to 1110 kW in power rated. And our 1,500 volt family is capable of 1130 to 1580 kVA. So while you are also taking advantage of standardized PV inverters and standardized battery inverters, also an additional advantage can be taken in the fact that this family of PV inverters and storage inverters are similar in their internal workings, and therefore gains an advantage of one product family for PV or storage to allow an ease of maintenance for operations and maintenance, and also a lot of the spare parts can be similar to each other. And advantages further, and what I've shown previously about connecting multiple inverters to a single low voltage winding, what we call the power station design, offers a compact solution of integrating onto a skid a complete solution of the DC connection and the AC output of the step-up transformer in a more plug-and-play. It allows to our customers supply chain reduction by utilizing Ingeteam as a sole source for all those multiple components, and ensuring that they all integrate together. It is plug and play because the DC comes from, in the PV, the combiners, or the DC, the battery system, and the output, that of the medium voltage transformer, the high voltage compartment within. The skidded solutions could be 1, 2, or 3 inverters, anywhere for up to 3.5 or almost 5 mega total of solution, depending upon which battery or PV inverters, the 1000 volt or 1500 volt line, you're taking into consideration. That O&M advantage and spare parts advantage it can be utilized because it is the same product family, allowing for that capability. And in that centralized solution, again, emphasizing that balance of system does have a cost savings. Finally, a couple references that we've integrated into the market has utilized for PV plus storage, plant in Spain, utilizing lithium-ion technology for batteries, and for this particular plant required ramp rate controls and also energy shifting as a control application. A PV firming application which Ingeteam has performed included on island in the Indian Ocean, as this example shows, the utilization of the PV plus storage system, and it predicts in advance. This one utilized our SCADA system as well, where the grid operator has the access into the plant. He or she has the capability to see the operating conditions, the access to frequency regulation for grid support applications of the plant through our SCADA. And here is actual data taken from installation in a real live recording through the data logger of the plant. This one again being the PV firming application. A few takeaways from the webinar. I emphasize that the AC coupling does allow standardized inverters, and therefore you get to take advantage of the DC inverters and the battery inverters to perform and optimize to each system. The centralized solution allows the reduced quantity of a battery size in a ramp rate control application, therefore a more cost-effective manner to design the entire plant compared to a distributed system. The standard inverters has advantages for O&M, for spare parts, for trainings of the technicians to maintain the plants by utilizing the standard inverters. And also finally, that compact medium voltage power station solution is an optimization of each individual PV or each individual battery plant for a total system, balance of system optimization.